My name is Chaitanya Krishna of Section ITA and my roll number is 19. And my topic for Tech Talk is a generalization of the binomial coefficients. Definition 1. The most basic. The most common definition of binomial coefficients is not the most useful or the most general. Most sources define the binomial coefficient brackets n comma k brackets close as brackets open nk brackets close equals n factorial by k factorial into n minus k factorial, for where n is a positive integer and 0 less than or equal to k, which is less than or equal to n. Call this definition 1. It turns out to be useful to replace the above definition with one that allows n to be any real number and allows k to be any integer. The definition 2, which is more general. The book Discrete Mathematics defines binomial coefficients as follows. First, define the kth falling power of r as r to the power of k equals r into r minus 1 and so on till brackets open r minus of k plus 1 brackets close. The kth falling power of r multiplies starts with r and multiplies with together k numbers, each being one or less than its predecessor. Given this notation, we can define the binomial coefficients as brackets open r k equals r to the power of k by k factorial if integer k is greater than or equal to 0, else it is equal to 0 if integer k is less than 0. Call this definition 2. Note the use of r rather than n to remind us that the top number can be any real number, not necessarily an integer. When definition 1 and definition 2 both hold, they give us the same result. When only definition 2 holds, the value can no longer be interpreted combinatorially. That is, it doesn't make sense to think of r things taken k at a time or choosing k things from a set of r items when r is not an integer or when k is negative. So why the new definition? Here are 4 reasons. Many theorems can be stated more simply in terms of definition 2. There is less need to include qualifications in theorem statements. For example, the cases k less than or equal to n and k greater than n can often be handled uniformly. Definition 2 turns out to be the correct generalization to allow many theorems to extend to more general arguments. For example, the binomial theorem extends to general exponents when binomial coefficients are defined this way. Sums can often be expressed as summations over all integers. The terms that you would otherwise need to explicitly exclude turn out to be 0. This simplifies formulas and reduces errors. The binomial coefficient r, k is a kth degree polynomial in R, which turns out to be very handy in proofs. It is often possible to show that two binomial coefficients are equal by showing that the corresponding polynomials agree at k plus 1 points and hence must be equal everywhere. Definition 3. Most general. Definition 2 is adequate for many applications, but here is a still more general definition. For any complex numbers, that is z and w, the binomial coefficient represented as brackets open z comma w brackets close can be defined as follows. Brackets open zw brackets close equals limit u tends to z into limit v tends to w is t of mu plus 1 by t of v plus 1 into t of u minus v plus 1. If we define z factorial for a complex number to be t of z plus 1, then definition 3 looks like definition 1, except for the limits. What's up with the limits? They are necessary to properly handle the cases where z or w are singularities of the t function. It is not obvious that definition 3 gives the same values as definition 2 when both definitions apply, but we will show that this is the case. The singularities of the t function occur at 0, -1, -2, etc. And so the limit in definition 3 is non-trivial when z or w are negative integers. If w is a negative integer, the limit is 0 because the denominator goes to infinity. We do not need to be concerned about whether z is also a negative integer because the limit in v is evaluated before the limit in u. If w is not an integer but z is a negative integer, the binomial coefficient is infinite because the denominator is bound but the numerator goes to infinity. This does not contradict definition 2 because that the definition only allows integer values of w. Suppose w is a non-negative integer. We show that definition 3 gives the same value as definition 2. First we apply the reflection identity to t of mu plus 1 and t of mu minus v plus 1. Then we have t of 1 minus u into t of mu equals pi by sine of pi mu, which can also be written as limit u tends to z and limit v tends to w, t of mu plus 1 by t of v plus 1 into t of u minus v plus 1 equals limit of u tends to z pi by sine of minus pi u into sine of pi of w minus u brackets close into t of w minus u by pi, minus which is equal to minus 1 to the power of w into t of w minus z by w factorial into t of minus z, which can be written as minus 1 to the power of w into w minus z plus 1 and w, which is equal to brackets of z and w. In combinatorics, the binomial coefficient is used to denote the number of possible ways to choose a subset of objects of a given numerosity from a larger set. It is so called because it can be used to write the coefficients of the expansion of a power of a binomial. In combinatorics, the binomial coefficient indicates the number of possible combinations of k objects from n. For example, the number of possible ways to choose two objects from a set of 5 objects is equal to brackets of phi 2 equals 5 factorial by 3 factorial into 2 factorial, which is equal to 5 into 4 into 3 into 2 into 1 by 3 into 2 into 1 into 2 into 1, which can be cancelled to get 5 into 2, which is equal to 10. Thank you.